Hi everyone, I am Narayana from Delhi Public School, Bhimavaram, HOD of Mathematics. Let us continue our class on the topic number systems. Before starting, let us briefly go through what we have learned in the previous class. In the previous class, under number systems, we have learned different types of number systems such as natural numbers, which are 1, 2, 3, 4 and so on. If you add 0 to natural numbers, you will get whole numbers, and to these whole numbers, if you add negatives of natural numbers such as -1, -2, -3, -4, -11, etc., you will get integers. To these integers, if you add terminating decimals such as 5.4 minus 0.5, also if you add decimals such as non-terminating and repeating decimals, for example 5.43 bar, apart from that fractions -5/9 to 1/3, also square roots of perfect squares such as square root of 4, square root of 9, square root of 16/25, etc. all are rational numbers which can be written in P/Q form. Let's see how to represent these rational numbers on the number line. Here you can see on the number line, first we have marked 0 in the center. To its right side we have positive integers with fixed interval. Similarly, on the left side you have negative integers which you can see. Apart from that, you can see some numbers which are like 9.3 bar, square root of 49 is 5/2, 2/3, -3, 1/2, -7, -9.5. All these numbers I can write them in P/Q form. For example, already you know these integers I can write in P/Q form by assigning denominator as 1. Already this is in, I can convert this into -7/2, which is in P/Q form. This is in P/Q form. This is in P/Q form. Square root of 49, which I can write it as 7. Again, I can write it as 7/1, which is in P/Q form. This also 9.3 bar can also be written. We will learn that is a decimal which is a non-terminating and repeating decimal. We will learn in the coming classes how to write such numbers in P/Q form. Now here this decimal -9.5, which can be written as -95/10, which is in P/Q form. Now my question is, do there are any numbers still you can insert on the number line? And the answer is yes. Still there are infinitely many numbers. I will show you. Root 2 I can insert on this number line. Root 5, pi, whose value is 3.1416 ... which is a non-terminating and non-repeating decimal. We will learn about such decimals later in the coming classes. So such numbers are there. Such numbers I cannot write them in P/Q form. Such numbers are called as irrational numbers. Today we are going to learn about irrational numbers. let us learn in detail more about irrational numbers. Before that, let us go through the definition. I have shown you already root 2, root 5, pi. These are some of the examples of irrational numbers. What makes them irrational numbers? Let us learn in detail. You can see here the definition. Irrational numbers. A number S is called an irrational number if it cannot be written in the form P by Q, where P and Q are integers and Q is not equal to 0. In the last class, we have learned some numbers which you can write in P by Q form. Now, today we are going to learn about the numbers which cannot be written in the form P by Q, where P and Q are integers and the denominator, which is Q, should not be equal to 0. I have already shown you some examples, root 2, root 5 and pi. Some more examples. Root 2, root 3, root 15, pi, 0.10, 110, 1110, 1110, ... These are examples of irrational numbers. Irrational numbers are denoted by the capital letter Q dash. As you know that rational numbers are denoted by the capital letter Q, we are representing irrational numbers as Q dash. Now, my question is, how many such irrational numbers exist? And the answer is, in fact, there are countless irrational numbers on the number line. There are infinitely many irrational numbers. Now, let us learn something more about irrational numbers. No. First remark is, every non-terminating and non-repeating decimal is irrational. Before going to this statement, in the previous class we have learned every non-terminating and repeating in the previous class. Here we had and repeating. I will give you one example of the previous class. For example, 2.34 bar, which can be written as 2.34444 ... This is a non-terminating, which you can guess with this ... Non-terminating means no end, and repeating means you can see here the digit 4 in the decimal part is repeating. It is a non-terminating and repeating decimal which can be written in P by Q form. But here, to be an irrational number, it should be non-terminating and non-repeating. Already I gave you one example in the definition. Let us go through some more examples. Here, this example already we have seen. Let us go through 0.10, 110, 1110, 1110, ... Here, in the decimal part, none of the digit is repeating. You may think that here 1 and 0 are repeating, but actually it is not. Here, 1 one time, then 0 one time. Here you can see 1 2 times, again 0 one time. Here 1 3 times and 0 one time. Here 1 4 times and 0 one times. Again next you will get 1 5 times and then 0. Yes? So here none of the digit is repeating. You can see here 1 is increasing. It is a non-terminating and non-repeating decimal. Similarly, you can see one more example, 27.53 5 double 3, 5 triple 3, 5 double 3 double 3 dot dot dot. And the next example is 0.21 double 21 triple 21 double 2 double 21 dot dot dot. Such decimals are called non-terminating and non-repeating. Non-terminating means with this dot dot you can find out that there is no end, and non-repeating means none of the digit in the decimal part is repeating. So such decimals you can write them in irrational form. Next remark is the square root of every non-perfect square is irrational. To go in detail, I want to recall in the previous class we have learned the square root of every perfect square. Here you have non-perfect square. In the previous class we have seen the square root of every perfect square is rational. I will give you one example. Square root of 4. Here 4 is a perfect square. Why? Because I can write 4 as a product of two equal factors which are 2 into 2. But now here we are going to discuss about square root of every non-perfect square. Non-perfect square means any natural number which cannot be written as a product of two equal factors. For example, 2, I cannot write 2 as a product of two equal factors. Similarly 3, similarly 5, 6, 7, 8, 10, all these numbers what I said, I cannot write them as a product of two equal factors. So such natural numbers are called as non-perfect squares. Let us go through some examples. Root 2, root 3, root 5, root 6, root 7, root 8, root 10, etc. all are irrational numbers because I cannot split 2 as a product of two equal factors. I can write 2 as product of two numbers such as 1 into 2, where 1 and 2 are not equal. Similarly 3 also, 5 also. 6 I can write it as a product of 2 into 3 or 3 into 2. 2 into 3, in this 2 and 3 are different factors. Similarly about 7 is a prime number, so I can write 7 as 1 into 7 or 7 into 1. 8 also I cannot write it as a product of two equal factors. Same thing about 10. Yes. Next thing. Now next remark is the cube roots of non-perfect cubes are irrational. Non-perfect cubes means any natural number which cannot be written as a product of three equal factors. For example, if you take 8, I can write 8 as 2 into 2 into 2. Therefore, 8 is a perfect cube because I wrote 8 as a product of three equal factors which are 2. Yes, but here we are going to talk about non-perfect cubes. What are those examples? Let's see. Cube root of 2, cube root of 3, cube root of 4, cube root of 5, cube root of 6, cube root of 7, cube root of 9, etc. all are irrational numbers because I cannot write 2 as a product of three equal factors. Similarly, as in case of 3, 4, 5, 6, 7 and 9. So here after 6 one more will come natural number, that is 8. I can write cube root of 8 as 2. which can be written as 2 by 1. So it's a rational number. Got it? Now next remark is, in the previous slide I have shown you on the number line pi. The value of pi is 3.1416 ... It means that in the decimal part the digits are not repeating. They are not in certain pattern. Therefore it is a non-terminating and non-repeating. It is a pi is actually, its value is 3.1416 ... and this is a non-terminating and non-repeating. Therefore pi is irrational. But in mensuration, while solving sums on circles, maybe your teacher told you pi, take it as 22 by 7 or 3.14. In that case, pi is not equal to 22 by 7 or 3.14. Your teacher may have said that pi is nearly equal to. Yes? So I can say that pi is irrational, while 22 by 7, which can be written in decimal as 3.14, is rational. But for our convenience, while solving problems in mensuration, we are considering pi is approximately equal to 22 by 7. But actually pi is irrational, whereas 22 by 7 is rational. I hope you have understood which numbers comes under irrational numbers. Now, here you can see on this number line I have represented 0, 1, 2, 3, minus 1, minus 2, minus 3, minus 1 by 2, 1 by 2. These are termed as rational numbers. Also you can see root 2, e, pi. These are irrational numbers. So usually this number line consists of two types of numbers. One is rational and the other one is irrational. All rational and irrational numbers together form the real numbers. This number line is called as real number line. Real numbers, all rational and all irrational numbers together form the set of all real numbers, and the number line is called as real number line. Real numbers are denoted by capital letter R. I hope you have understood. Now let us solve some sums which will make you understand the concept in a better way. Let us see the first example. State whether the following statements are true or false. Justify your answers. First question is, every irrational number is a real number. Through our discussions, it is true why it is true. Already we have learned that real number is a combination of rational and irrational numbers. So every irrational number is a real number. Yes, because every real number, either it is rational or irrational. It is classified into two types, rational and irrational. Therefore, our statement, every irrational number is a real number, is true. Let us go to the next question. Next question is, every point on the number line is of the form root m, where m is a natural number. You know, already I have shown you on the number line different types of numbers. Whether all those numbers can you write in the form root m, where m is a natural number? The answer is false. Why? Let me explain. Because when you say false, then you give at least one counter example which proves your statement why it is false. I said false. I can give you countless examples. On the number line, you can see negative integers such as -1, -2, -3, -4, and so on. I cannot write them as a square root of some natural number. Here m is some natural number. It is not possible. Whereas 0, 1, 2, 3, 4, 5 and so on, 5/6, all I can write as in the form of square root of m, where m is a natural number. Yes, you can give at least one counter example. I have given you many examples because -1, -2, -3, -4, etc. cannot be I cannot write this, for example, -1 as a square root of some natural number. It is not possible. Yes? If it is, if you take 2, I can write it as a square root of 4, where 4 is a natural number. But for negative integers such as -1, -2, -3, -4 and so on, I cannot write it as a square root of some natural number. Therefore, the answer is false. Yes. Let us go to the next question. Now the statement is, every real number is an irrational number. I hope you have guessed the answer. The answer is false. Because, as you know, real number is classified into rational and irrational. I will show you through tree diagram. Real numbers are classified into rational and irrational. But here the statement is, every real number is an irrational number. It is false because few real numbers are rational as well. So this statement is false. Let's go to the next question. Let me read the question first. Are the square roots of all positive integers irrational? If not, give an example of the square root of a number that is a rational number. Let us look into the first part of the question. I will read once again. Are the square roots of all positive integers irrational? First, let us find out what are those positive integers. You know very well the positive integers are 1, 2, 3, 4, 5 and so on. Now, for these positive integers, we have to take the square root. If you take square root, then the resulting answer is irrational every time. If it is every time irrational, then the statement is true. But it is not. For example, I will give you square root of 4. Square root of 4, I can write 4 as a product of two equal factors, which is 2. So its square root is 2, whereas 2 is a rational number. If you start with positive integers 1, square root of 1 is 1, which is a rational number. Square root of 2 is irrational number. Already we saw in today's concept. Next, root 3 is an irrational number. But root 4, which is 2, is a rational number. I can give many examples. There are integers such as, positive integers such as 1, 4, 9, 16, 25, etc. All these positive integers when you take its square root, you will get the square root value as a rational number. Yes? So, therefore the answer is no. If not, give an example of the square root of a number that is the rational number. Answer is no. If the answer is no, we have to give an example. So here I have given 3 examples. Square root of 4 is equal to 2, which is a rational number. I hope you have understood. Now, as we have seen, root 2, root 3, root 5, root 7, root 8, etc. cannot be written in P by Q form. Therefore, they are irrational numbers. In your 8th standard, you have learned to find out the square root of root 2, root 3, root 5 using division method. But in this class, we are going to learn how to locate these irrational numbers on the number line. First, we will learn how to locate root 2 on the number line. Let's see. First, what we have to do is draw a number line and mark the center point as 0. Next thing, what we have to do is mark right side of the 0 as 1 and the left side as -1, which you already know. To the right side of 0 are positive integers, which are 1, 2, 3 and so on. To the left side of 0, the negative integers, which are -1, -2, -3 and so on. But we will mark 1 on the right side of 0 and -1 on the left side of 0 with equal interval. Yes, you can see clearly on the smart board. But what we are going to do is we will consider 0 and 1 only to locate root 2 on the number line. We are going to ignore -1. We won't be considering -1 for our purpose. Next, what we are going to do is, with same length as between 0 and 1, draw perpendicular to point 1 such that new line has a length of 1 unit. I will explain here. Yes, whatever the length is there between 0 and 1, we have to take same length and we have to draw a perpendicular from 1. Already you have learned in your smaller classes how to draw a perpendicular to a given line on a given point. A perpendicular means a line which intersects the given line at a given point with an angle of 90 degrees. Yes, here. So whatever the length is there between 0 and 1, same length you have to draw a perpendicular at 1. Yes? So, from 0 to 1, its length is 1 unit. Similarly, the perpendicular which has drawn from 1, its length is also 1 unit. Next, what we have to do is, now join the point 0 and the end of new line of unity length. It means that take 0 and the end of this perpendicular is here and join with a straight line. Now, if you look, you can see here a right angle triangle. Let us name this end point as A. Yes, this one as B and 0 as C. Now the triangle formed is ABC is a right angle triangle at B. I will show you on the screen. A right angle triangle is constructed, which you can see on the green board. Next, what we have to do is, let's go through. Yes, this is how you will get a right angle triangle. Now, let us name the triangle as ABC. Yes, we gave a name as ABC, such that AB is the height of this triangle. AB is the height. Height is also called as perpendicular. This AB, BC or CB is the base of this right angle triangle, and AC is the hypotenuse. AC is called hypotenuse. As you know, in a right angle triangle, this side opposite to 90 degrees. Here I will show you. Here you can see that angle B is 90 degrees. In a right angle triangle, this side opposite to 90 degrees is the largest side, and the largest side we named it as hypotenuse. So here AB is the perpendicular or height, BC is the base of the triangle, and AC is the hypotenuse. I hope it's clear. Now, you know the length of AB is 1, length of BC is 1. Let's read this. Now, length of hypotenuse, that is AC, can be found by applying Pythagoras theorem to the triangle ABC. Now, what we are going to do is, we are going to find out the length of AC, which is √2, you can see, which can be calculated using the Pythagoras theorem. Here you can see value of AC is √2. Let us get it. You know, according to Pythagoras theorem, in a right angle triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides, which means here AC square is equal to the other two sides are perpendicular and the base. Here the perpendicular is AB, so AB square plus, and the base is BC, so BC square. This is according to Pythagoras theorem. I will repeat the statement of Pythagoras theorem. In a right angled triangle, the square of the hypotenuse is equal to the sum of the squares of other two sides, and the other two sides are perpendicular and the base. Now here we are going to calculate AC. AB, you can see from the figure, length of AB is 1 unit, so it becomes 1 square plus BC length is 1 unit, therefore 1 square. 1 square is 1 and 1 square is 1, so 1 plus 1 is 2. We got AC square as 2, therefore square root of AC becomes root 2. Hence, using Pythagoras theorem, we got the length of AC, which is the hypotenuse, is root 2. I hope it's clear. Now, what we have to do is take your compass, take O as center and radius as root 2, radius as OA, which is root 2. Now you keep center as O and draw a arc towards right side of 0. I will show you, you will get an idea through the diagram. Yeah, here you can see. Now with AC as radius, take the compass, take AC as radius, which is root 2, and C as the center. Here C is the center, take this as center, and an arc on the same number line. You have to draw an arc on the same number line. This is your number line towards 1. Yes, when you draw an arc, you can see here, yes, take this length and take O as center, draw it, you will get a point, and that point denotes root 2, which is, so length of O, you call this point as D. So length of OD is same as length of OA. Hence, we have located root 2 on the number line. Since AC is the radius of the arc, you have to take AC as the radius of the arc, and hence CD, this C to D will also be the radius of the arc. So length of AC and length of CD are going to be equal. Hence, whatever the you want to locate, we got the answer. I hope it's clear. Hence, this D is the representation of root 2 on the number line. I will do here, yes, with this, I will extend this. Take O as center with your compass and radius as OA, which is root 2. Take O as center towards right side of 0. Just draw an arc and call that arc, that point as D. So length of C to D, yes, is root 2. I hope it's clear. Now we are going to learn how to locate root 3 on the number line. Let's see. Now I will use the same, whatever we have done, root 2. Now in the previous case the base was BC. Now the base will be AC. I will repeat the same procedure. What I will do is, I will take A as center. At A I will draw perpendicular to AC. How? I will show you on the screen. To locate root 3 on the number line. Now, so what I will do is, right now I will take, in the previous case the base was BC, whose length is 1 unit. Now I will take base as AC, whose length is root 2. Now at A I will draw perpendicular. You can see here the perpendicular is EA, whose length is 1. Next what I will do is, I will join E and C. Again you will get a right angle triangle. I will show you. Now we need to construct a line which is perpendicular to line AC. For AC we have to draw perpendicular from point A, such that this new line has unity length, and let's name the new line as AE. The length of the new line, which is the perpendicular at A, is of 1 unit. I hope it's clear. In the next step we will join E and C. Yeah, you can see here E and C is calculated, and we have repeated the same steps. Now here you can see that this EAC is a right angle triangle at vertex A. Yes, now then EC becomes the hypotenuse. Again we are going to use the Pythagoras theorem. By Pythagoras theorem we will get the value of EC as root 3, which I am going to explain on the board. Now join C and E. Got it? The length of line CE, this one, could be found out by using Pythagoras theorem in right angle triangle EAC. Let's see, when you use the Pythagoras theorem, so the length of line EC is found to be root 3 units. That I am going to explain on the board. Let's see. Yes. Again here we will draw a perpendicular of 1 unit. Next we have to join this. So you have to name this as E and its length is 1. Now I am going to draw this right angle triangle here for our convenience. Now you can see this right angle triangle here. CA or AC is root 2 units, A is 1 unit. Now I am going to calculate the length of CE, which is the hypotenuse, using the Pythagoras theorem. Yes, let's see. As EAC is a right angle triangle at vertex A, therefore by Pythagoras theorem, here the side opposite to 90 degrees is CE, which is the largest side, and that is the hypotenuse, and the other two sides, one of them is perpendicular, the other one is the base. Yes, therefore by Pythagoras theorem, EC square is equal to, yes, AC square plus AE square. Therefore, EC square is equal to AC length is root 2. So root 2 whole square plus AE is 1 unit. Therefore 1 square. Therefore EC square is equal to root 2 whole square is 2 plus 1. Therefore EC square is equal to 3. Therefore EC is equal to root 3. You can see, therefore we got EC value as root 3. Next, as usual, what we have done in the previous case, to locate root 2 on the number line, same thing we will do. Now what I will do is, I will take my compass, I will take O as center and radius as CE, which is root 3 units. Now I will draw an arc towards the right side, yes, and somewhere you will get here. I will show you in the next screen. Here. Now with C as center, take your compass, take C as center, and EC as the radius of circle, E to C or C to E. Cut an arc on the number line. Yes, on the number line you have to cut an arc. You can see here. Yes, and we will call that point as F, and mark the point as F. Since OE, this OE is the radius of the arc, hence this OF or CF is also the radius of the arc, which are equal in length. Hence F will represent root 3 on the number line. I hope it's clear to you. Now what we will do is, so far we have located root 2 and root 3. Now we will see how to locate root 5 on the number line. Now here you can see, here I have taken a number line. Yes. So what I will do is, I will show you on the board. First you mark 0 in the center, towards 0 positive integers and towards left side of 0 negative integers. But for our convenience we are going to consider right side of 0. So 0, yes, this 0 I will call it as O. I will consider here to here. So length of OA becomes 2 units. Yes. Now what I will do is, at A I will draw a perpendicular of length 1 unit. And call the end of this new line as B. Next I will join O and B with a straight line. Clear? Now here you can see a right angle triangle OOAB at vertex A, which is 90 degrees. The length of OA is 2 units and the length of the perpendicular AB is 1 unit. Again I am going to apply the Pythagoras theorem. Here OAB is a right angle triangle at vertex A. Therefore, by Pythagoras theorem, here the hypotenuse is OB, therefore OB square is equal to the length of the other two sides are perpendicular and the base. Here the perpendicular is AB and the base is OA. Therefore OB square is equal to OA square plus AB square. Therefore OB square is equal, here the length of OA is 2 units. Therefore 2 square, and the length of AB perpendicular is 1 unit. Therefore OB square is equal to 2 square is 4 plus 1, 4 plus 1 is 5. Therefore OB square is 5. Therefore OB is equal to root 5. So we got the length of OB as root 5 using Pythagoras theorem. Now what we will do is, we will take our compass, we will keep it center as O and radius as OB of length root 5, keeping O as center. Towards the right side of 0, we will draw an arc on the same number line, and which will meet the given number line at point P, which is root 5. I hope you have understood how to locate irrational numbers such as root 2, root 3, root 5, root 7, root 8, etc. on the number line. Now it is the time to briefly revise what we have learned in today's class. Today we have seen that on the number line there are numbers which you cannot write them in P by Q form, and they are called as irrational numbers. A number S is called an irrational number if it cannot be written in the form P by Q, where P and Q are integers and Q is not equal to 0. Yes, these are some examples we have seen. Here we have seen that every non-terminating and non-repeating decimal is irrational. These are the examples. Next we have seen the square root of every non-perfect square is also irrational, and these are the examples. We have seen, apart from that, to locate root 2, root 3, root 5, etc. on the number line also. Next, the cube roots of non-perfect cubes are also irrational, and here are the examples. Also, we have seen that pi, whose value is 3.1416 ... which is actually a non-terminating and non-repeating decimal, is also an irrational number, because all these types of numbers I cannot write in P by Q form, hence they are termed as irrational. Yeah. Now let us go through diagrammatic representation of real numbers. As you learned today, real numbers is the combination of all rational and all irrational numbers. Here you can see real numbers are broadly classified into rational numbers and irrational numbers. So every rational number is a real number, every irrational number is a real number, but every real number is not a rational number. Every real number is not a irrational number, because rational number is a combination of, real numbers are the combination of rational and irrational. And in rational, already we have learned in previous class, you have natural numbers, whole numbers and integers. Apart from that, today we have seen how to locate irrational numbers such as root 2, root 3, root 5, etc. on the number line, and we have used Pythagoras theorem. Today I am going to give you an assignment. Please complete this and send to me on the given email ID which you can see on the screen. Today's assignment is locate root 7 on the number line as well as locate root 8 on the number line. Please complete this assignment and send to me on the given email ID. I hope you have understood. Still, if you have any queries, please give a missed call or call to the number which is on your screen. Thank you very much.